All right, let's talk about the invisible architecture that runs our entire world. It's under the hood of every app, every website, every single line of code. We're talking about the hidden rules that give code both its structure and its meaning. Okay, so take a look at these two bits of code. On the left, you've got a syntax error. It's just broken grammar. There's a piece missing, and the computer just throws its hands up and says, I don't even know what you're trying to say. But now look at the right. That's a semantic error. The grammar is technically perfect, but the meaning, it's complete nonsense. It's like telling your program, hey, take this word hello and stuff it into this little box that's only designed to hold numbers. The structure is fine, but the logic is impossible. And that difference right there is everything. And this really gets us to the two fundamental pillars of any language, whether we're talking about English or Python. Right, so let's put it this way. Syntax is the blueprint. It's all the rules about how to put the beams and walls together. If you follow the blueprint, you get a structure that won't fall down. Semantics, on the other hand, is about what that structure is. Is it a house? Is it a bridge? Or is it just a jumbled mess of parts that doesn't actually do anything useful? That's the difference. You know, when a friend sends you a text message that's full of typos, your brain just kind of fills in the gaps, right? You get what they mean. A computer, no way. It has zero ability to guess your intent. For a machine, any tiny mistake, any little deviation from the rules isn't a typo, it's a critical failure. And that's exactly why we need a formal, crystal clear, unambiguous rulebook for code. So how in the world did computer scientists manage to create a perfect rulebook like that? Well, the system they came up with is actually pretty elegant. The big breakthrough really came back in the 1950s with pioneers like Noam Chomsky and John Backus. They basically designed a sentence-generating machine on paper. It was a formal system that could spit out every single valid sentence for a language. And, just as importantly, it would be impossible for it to create an invalid one. And that system is called Backus-Naur form, or just BNF. Honestly, the best way to think about it is like Mad Libs, but for programming. You have two kinds of things. Non-terminals, which are the placeholders, the blank spots like adjective or statement. Then you have the terminals. Those are the actual words and symbols you can plug in, like if or a plus sign. The BNF rules tell you exactly which terminals can go into which non-terminal blanks. So you start with one big abstract concept, like program, and you just follow the rules, step by step, replacing the placeholders with more specific placeholders, and then eventually with actual code. That whole process is called a derivation. And you can see it right here in action. We start with that high-level program. The rules let us turn that into statements, which becomes a single statement. We keep going, following the rules, swapping out these abstract ideas until, poof, all that's left are the terminals, the real words and symbols that make up our final, syntactically perfect line of code, A equals B plus const. But let's be honest, trying to track all those text replacements is a little clunky. There's a much better way to see it. If you visualize the process as a kind of family tree for the sentence, what we call a parse tree, the whole structure just snaps into focus. You can literally see how every part of the code grows out of that initial program root. Okay, so having this rulebook is fantastic, but what happens if one of the rules can be read in two different ways? This brings us to a huge problem, ambiguity. For a computer, ambiguity is a complete showstopper. Think about it. It's like telling your GPS to take the next left, but there are two lefts right next to each other. Which one do you take? A computer can't just guess. It needs one and only one right answer. And here's the genius solution. An ambiguous grammar might not be clear about the order of operations in a math problem, but a well-designed, unambiguous grammar builds that logic right into the rules themselves. It literally forces the parse tree to grow in a specific shape, making it impossible for the computer to get it wrong. It ensures that division always happens before subtraction, every single time. No guesswork needed. But here's the catch. Even a perfectly crafted BNF grammar has its limits. There are some really important rules that it just can't enforce on its own. So for example, BNF is great at telling you if you've written a line of code with the correct structure, but it has no memory. It can't look back a few lines and check if you actually declared a variable before you tried to use it. For that, you need context. You need a bigger picture. And this is where we need a more powerful tool, something called attribute grammars. The best way to picture this is that we're adding little sticky notes to our parse tree. These notes, or attributes, carry extra information around, like, hey, this variable is a number, or this one is text. So as the compiler builds the tree, it can read the notes and catch those more complex, context-sensitive errors. So we've got this structure down. We've even figured out how to add context. But that still leaves one huge question. How do we formally define what the code actually does? What is its meaning? Well, computer scientists came up with 3 main ways to tackle this. First, you've got operational semantics. This is the most straightforward. A program's meaning is just a description of what happens step by step when you run it on a computer. Then there's denotational semantics, which is way more abstract. It defines meaning using pure mathematical functions. And finally, there's axiomatic semantics, which uses formal logic. It's all about proving what must be true before and after a line of code executes. Okay, I know what you might be thinking. This is all getting pretty deep into theory. Why does any of this abstract stuff really matter? It matters because these formal methods are the bedrock of everything. They're what guarantees that code written by a programmer in Brazil on one type of computer will behave the exact same way for another programmer in Japan on a completely different machine. They're the universal rulebook that makes global software possible. All right, so let's boil it all down. What are the big takeaways here? Number 1, syntax is the structure, semantics is the meaning. They're different, but equally important. 2, tools like BNF and Parse Trees are what give our code a predictable, reliable structure. 3, ambiguity is the absolute enemy of computing. Computers need clarity. And finally, formal semantics is our way of proving that our code will actually do what we think it's going to do. This whole invisible framework is what makes our digital world work. It's this silent, logical engine that powers everything we do. And it leaves you with a kind of fascinating thought, doesn't it? We work so hard to create these perfectly rigid, logical, unambiguous languages for computers. So what can that perfect logic teach us about the power and maybe even the beauty of our own messy, creative, and wonderfully ambiguous human languages?